everything is just going to be recorded. Okay, so let's look at this example. I like to just go with this example with Excel, because this example is something that we can go ahead. We need to just use Excel spreadsheet normally, to be honest, and it's good to just see how it works and how we can calculate things ahead. Okay, so let's just go through with the example. You can see here there is a figure. Sorry, the figure below. This kind of like the figures that you can see in this table at the bottom. Shows the river. Hang on. Okay, so you can. Oops, sorry. So this figure at the bottom, you can see all over the year. It shows the monthly inflow in the river in the unit of million cubic meters. Okay, so for example, April is like the 3.15 million cubic meters until March of the following year is 6.83 million cubic meters. Just let you know that normally the annual water year is started from September. Sorry, start from October. We say like the water year is because the cycle is going to finish. I mean, the demand is going to be high until the end of the summer, and from the October we have a new water year. So the cycle normally start from that, and the rainfalls also start from that one at that time as well. You know, like the semi-arid region, for example, let's say. But anyway, this is like the inflow. For example, April is like 3.15 million, May is like 2.53 million cubic meters, and there are some. This is like the inflow. Anyway, for the demand or supply, you know, in the second line, to be viable, the reservoir must provide at least 5 million cubic meters per month throughout the year. Okay, so this is something that, let's say, the demand could be like the water irrigation, or could be for, let's say, for domestic use, or for I think these two like the main purpose, or industrial as well. We need to just provide that 5 million cubic meters per month, and assuming that a month is going to just assume to be like the 30 days, rather than, you know, we have like a February like the 28, 29 days and similar, but assuming that we're just going to consider everything for 30 days per month, and a constant compensation flow 0.81 million cubic meters per month must pass through the dam. This is called compensation flow. In some references you might see as a like the environmental flow. It says to make sure that the river is survive and live, you need, you know, for aquatic life that you have in the river, you cannot just completely stop the water going downstream. If you have like a small river, obviously that can be easily resolved by, you know, regulations, for example, national regulations. I wanted to let you know that if the downstream of like the reservoir is another country or another countries or more than one country, you have a some sort of like a water policy, international water policy in place as well. Because, you know, for example, Nile, for example, river in Africa, started from like the middle of the Africa and eventually just went through like a few countries, eventually Egypt, and eventually discharge or join the Mediterranean Sea. But that caused a problem. That compensation flow needs to just be satisfied for all the demands downstreams as well. And in many countries, you might see this kind of like the international water policy in place, and sometimes it causes a lot of tension and cause a problem issue between the countries. And it was very popular at the beginning of the century. It was popular that they said the new century, like the century that we have the war of the water. Fortunately, so far it wasn't very serious. But if we have like a drought in the future, it might cause a serious. But still, as far as I can see, like for example, Egypt in Africa, they've got some sort of serious problem with the dam construction for the countries upstream the Nile, the Nile, sorry, and some other countries as well. In the Middle East, we have some countries like the Euphrates and as there are two main rivers in like the Middle East that start from Turkey and Syria. Start from Turkey, both of them, but pass through the Syria and Iraq. And both downstream countries are highly dependent of the water supply from the upstream, from the mountainous area in Turkey. However, especially in the Turkey, they've got a lot of like a large construction, a large plan for construction of the big dam reservoirs, and that caused a very negative impact for the downstream. So and so that sort of like international water crisis has already started. I mean, but anyway, so this is something that potentially might just cause a lot of tension between the countries as well. But if there is something inside the country, it's not like a big issue. It could be like I'm saying not big issue, but in some cases it could be like a big issue between different like the groups in the country. If the water supply for different like the provinces or counties, or let's say like the regions, other peoples might just complain, and there might be some sort of like a crisis even inside the country. But inside the country could be resolved better than the like international crisis between the countries. But anyway, so just bear in mind for most of the like the rivers that the transfer between the countries, the water, this kind of like the cause of like the water supply has been a big issue. So I wanted to just give you some heads up about this kind of like a compensation flow or environmental flow. Anyway, so you need to just know like or aware of whatever the background, the policy, or the potential crisis that might happen. And when you're just going to design this, you need to just pay attention to all these points as well. So when you're just going to have any source of that, some of them is not very easy to calculate this. For example, we say here as simple as the like the 0.81 million cubic meters. In some cases, it could be really complicated. And and all the countries must, if the water supply source from their own country, they are very reluctant to release the water to the downstream countries. However, based on the international law, all the countries from the source, they have to release water, because of the catchment is not only the upstream. The catchment of the water supply is the whole area from the upstream to downstream. So obviously, all the relevant people have the right to use the water. So anyway, so that is something we want to see. So anyway, so this compensation must pass through the dam, including the month that when the flow passes over the spillway. Assuming that the reservoir is initially full and it must be refilled by the following April, let's say. So we just trying to just have like a similar trend or the consistent trend. All months are equal length. Using the tabular method, determine whether or not the reservoir could sustain the demand during this kind of like the drought year. A, B, the volume of the storage required, and C, whether the flow is passed through the dam or not. Okay, what do you think about that? How we can just go ahead for this problem? Any idea? Just think for a moment. So obviously we need to just have a spreadsheet. I'll just create a spreadsheet here. Oops, sorry. So we need to just have all the month and the flow. So let's say I've just done this one here for you. You create like the Excel, all the like the values here, from April to the March, and all the figures. I'll just put it here. Okay. So first of all, we need to just have like the first section. Let's see what is the first section. Whether or not the reservoir could sustain the demand. So we need to just during this drought year. Okay, this year is drought year, so it's not like the floods. So just pay attention. Once the point here is to calculate the demand, or you want to see if the yield is sustained or not, you need to just look at the driest year. If you are looking at the control of the flood through the spillway and see if the flood control has got a capacity or not, you need to just look at the wettest year, okay, or the wet year. You are not supposed to just look at the flood through looking at the drought years or the dry years. You know why? Because the dry year you have no problem for the flood. In the dry year you have a more concern for the water supply. On the other side, for the flood, you are supposed to just look at the wet years, not like the dry years. Is that clear? Okay, so we need to just use the accumulative value of this figure, the total sum. So we have these ones here. So let's see if I can just use this as a, I think this one, because I like to just use a lot of columns here. Okay, so accumulative value here. So what I'm just going to use is this one, and this one, is the previous one plus the new values. So I can, click here and double click here. So get all values here. So the total at the bottom is, so the sum of the values here, can you see here? This is the 75.1 0.1 million cubic meters is the total. So you can see the totals here. Okay. So if I'm just going to just consider the demand, the outflow, I'm just going to put the outflow here. Outflow here. So the demand, outflow is like the 5 plus 18, sorry, 81, 0.81 is like a 5.81. Can you see here? Sorry. Okay. So I can use it here as well. So the outflow, and the outflow, I'm just going to use the accumulative value as well. So I like it for the next steps as well, not only even necessarily for this step. So this plus this one. So we're just going to use this one. Okay, anyway, so that figure is the same. So because the accumulative flow is larger than the outflow, we can say yes, definitely this sustain. And this is for the first section. The second section is saying that the volume of the storage required. Okay, let's see how we can just calculate that one. We need to just calculate another the difference of the storage. So I'm just going to put another things here. The difference of the storage, I can just take the difference between the inflow and outflow. Inflow minus outflow. Okay, can you see here, for example, in April, the storage will be emptied by 2.66 million cubic meters. So I'm just going to use this one. So you can see here. And then you need to just use the accumulative value of that one to see that kind of like the, let's just make it a little bit smaller. Okay, so this is like the minus 2.66. The following month is this one plus this one. Can you see here? So again, oh, okay, so this is going down to like the minus 21.9, and then it's increasing because the storage is like the recovering, or is like filling the reservoir. Can you see the inflow is higher than overtake the outflow? But until this month, it's like the outflow is like the higher than. From October, we can see the inflow is higher than the outflow. But from April until September, the demand or the outflow or is higher than the inflow. And makes sense, you know, this is like the wet season or autumn or spring, and you can see, or sorry, or autumn or winter. But over the summer or spring, we have like the demand is higher and we don't have a lot of rainfall. So as a result of that, so this is like the minus 21.9. This is a maximum value, and then you can gradually just decrease the value here. Okay, so you can say this is the amount of the storage, 21.9. So if you want to just see this one, this is the figure that we can have. You can just have like a plot of the outflow. You know, for example, you need to just come in here. Not all of them, to be honest. So I don't need this one. It just creates two in here. For the first one, I like to just have the variations between the absolute figure. That's just empty. Okay, so I need this one. I need this one as well. Change in variation, I don't need this one here. And the same for accumulative as well. Can you see? This is the inflow and outflow. That's as simple as that. And for the top graph, so this for the bottom one. For the below one, I like to just keep these two and remove the other ones. Can you see here? Very simple. This is the accumulated value. Can you see this is the inflow, outflow, accumulative inflow, and accumulative outflow? As simple as that, you can see this is the October, what sort of changes is going to happen. Okay, that's like the section one. Not section one, it's like the, okay, so section B. Whether the flow passes over the dam spillway. Okay, let's analyze that one. Can you see here, this is like the accumulative outflow and accumulative inflow. At this point, they can get to the same point in let's say in January. Can you see here in January, they can actually set to this point, and in February and March and April, the accumulative inflow overtake accumulative outflow. So you can see in the last 3 months, so you can see here just trying to just get more value here and just increasing like in January, February, March. So you can see here in January, not exactly overtake, but in here, so sorry, not in March, it has to be decreased. Let me just stop this one here. And the same for here as well. Okay, so you can see here only for 2 months, in February and March, you can see the sum, the accumulative sum is likely going to be positive. So at the end, 5.38 million cubic meters is going to be wasted through the spillway. So just pay attention to this point. So a little bit in February and the rest in the March. You can see here, this is something happens, but until January, the result is even negative. But in February and March is passed through the threshold. And the same here you can see, but this is like the reservoir that we have. We need to just make sure, you know, for example, up to this point, we need to just have a reservoir. And you can see here, the reservoir comes like whatever capacity it has, they start from emptying until like the minus 21.9, and eventually when it's filling, it get to 0, and this is like it becomes full. Okay, so that's like the example 1. Is there any question? No question? Okay, let's just move to the example 2, or okay, so whatever is just written here, we just explained already, and that's the things is going to happen. Example 2, we have, using the same data in the previous example, draw the mass curve and determine the storage required to meet the given demand. Investigate the maximum possible demand that could be obtained, any additional storage requirement, and for convenience, assuming that days like the 30 days. Okay, so we need to determine the storage requirements to meet the given demand. For this question, so see what you can see. And section B, investigate the maximum possible demand that could be obtained and any additional storage required. What do you think? First of all, let's talk about like the section A. Using the same data in the previous example, draw the mass curve that determine the storage required to meet the demand. So what do you think? So obviously the section A is like the mass curve that we already plotted. Did you notice? We already plotted this one. This is almost like the accumulative value, and this is the absolute value of the demand and supply. We just plot that one here. Okay, so this is like, for example, section A. So the way that we can just identify the storage, so it looks like, for example, the difference between here to here, the vertical distance. I don't know if I can just write it here, but let's just look at the answer here. I'm just going to show you. Here, can you see 21.9? So this is like once it's plotted here. So you're just going to get it here, 21.90 and 5.38. But this is the capacity that you can get to this to just fulfill the demand, and this is like the spillway that is going to be overflow from the reservoir. Okay, so let's just get back to the example. Okay, so that's section A. Section B, investigate the maximum possible demand that could be obtained. Any additional storage requirement. Okay, so if we want to just, for example, in this case, this amount is wasted. So we want to just see if we want to just use here what we can do. So something like the one good approach is that, look at here, rather than, can you see the line OC? OC is the demand. If you just have like the line OD, this is the like the maximum. OD, the dashed line. Exactly, if you have like the demand is going to be dashed line, the total inflow is going to be used completely at the point D. Okay, so in that case, as simple as that, 21.90 needs to be added with this figure. Can you see? But let's just do this one a little bit more by using some sort of like a formula for that. So you can see here, so and you can see here, if it's explained here in here, oh sorry, in here that, so the CD can be added because it's wasted, so the reservoir could support a slightly higher demand as indicated as dashed line OD. Okay, so what we can just do, calculate this one. Let's look at our figures. So our figures is that currently we have this one, sorry, let's just look at here. We currently have this one. Remember, this is the something that we had. This is the, this figure divided by 12. This no surprise, is exactly the same figure that we accumulated here. This is a monthly one, but the inflow, if we divide it by 12, So just like the 6.25. If every month the demand is going to be used 6.25, we will exactly have that sort of like the calculations in the we will have 6.25. If you have 6.26 million cubic meters, we will exactly have the same as that one, or 5.45. 5.45 is for the with the compensation flow deducted. So if you just reduce the compensation or deducted or taken away the compensated flow, we will have like we can supply 5.45 million cubic meters for this sort of like the situations, and in that case you need to just have like a 24.60 million cubic meters. Okay, just pay attention to this point. This point is something very interesting. Even myself, I just make a mistake. I made a mistake in here. I said like let's just accumulate 21.9 plus this one. However, the new reservoir is supposed to be this one because 21.9 plus 5.38, it becomes this one. No, this is not the answer. The answer is that AE until A is supposed to be 24.60, not 27 point, and get the sum of this kind of this figure, and this figure cannot give you the answer, so it's a wrong answer. So how can we calculate this one? You might just have a question. Okay, so how can I just calculate this one? Because it's like in geometry I might just made a mistake. I can calculate the slope of this line and get like the point E, but this is like a little bit sophistication, so it might be just a little bit complex. But one other approach is that you can repeat exactly the same procedure. Okay, let's just get back to this kind of like the Excel calculation. You can just do exactly the same procedure, but this time rather than using this value, use this figure. Okay, so what I do, I mean, in the reference, this kind of like it just mentioned that figure. It didn't explain anything in detail, but I'll just show you how just gonna go ahead with that one. So rather than like put in 5.81, you can just use this figure. Oh, sorry. Paste as a special as a figure. Okay, so I'm just gonna use it here. Okay, so so you can see here the sum of the whole is likely the same. Okay, can you see here? Okay, so let's get back to here. Okay, so and the same, the change, everything automatically updated. Oh, can you see here? It's automatically created here. 24.59 is exactly the one. I just have like a more accurate value here than the one reported in the reference book in this example. But the highest difference, negative one, is like a 24.59. So the one that I just created here. So what unfortunately the book did not explain here. It says okay, it has to be like the AE, and AE's length is like a 24.60 million cubic meters. But this is like the way that you can easily calculate. I just put like this figure as an outflow, and the same procedure, just copy and paste it, and automatically the new figure is calculated. Okay, so this is a one example that we have. Just please pay attention. This example is very important. You need to just carefully understand how it works. Is there any question? I think I'll just upload that figure into the sessions in week 8.
Excuse me,
yes,
sir.
Yes, please. Yes, Amara.
Could you please repeat from where 5.45 come?
This one.
Yeah.
Yeah, let me just bring the calculator. Where's the calculator? Okay, so that's a good point. So we said that if the total demand of the 6.26 million cubic meters needs to be, as a new total demand needs to be taken to make sure that all the water is used. Is that clear, 6.26, Amara?
Yes, sir.
Okay, so remember what was the compensation flow? How much was that? Remember? 0.81 million cubic meters. Remember?
Yes.
Yeah. Okay. So it says that 6.26 minus 0.81. You know, that's the compensation. Here it says that this is the flow with the compensation flow deducted. Okay. The way it's written is that I would say that it should say, okay, this is the flow minus compensation flow. Doesn't matter. So that's the figure. So it says that this one without the compensation flow. Okay, this is like, you know, this is called yield. Yield is the one that we just count on that as, you know, as a water authority or decision makers, that you can rely on this amount of the water per month to give it to the customers. You know, if you have a customer, you say, okay, this is the amount that I can give you the monthly, rather than like a 5. You know, for the previous example, it was 5 million cubic meters per month. So you can say like a 5.45 million cubic meters per month can be allocated as a result of this kind of like the increase. If you just increase the dam by a slightly higher, you know, if you increase the dam capacity to just collect, you should be able to just do this one. And something very important is that in some cases you might just find something very interesting. You might just might say that, oh, it's very interesting. If we increase the dam reservoir by 24.60, I would be able to just allocate more water. If I just gonna increase or decrease less, what would be the figure? For example, let's say I was saying that 21.90 million cubic meters, I would be able to just save like or to have a yield of the 5 billion cubic meters per month. If I have like a 24.60, this figure, where is that? Sorry, this figure, I can have like this amount of like a yield. But the question here is that if you have like the other figures, I mean, this is the maximum one. If you have other figures less than this or even less than this, the amount that you can save is less. So if you can plot the variations of uh, uh, the variation of the yield and the variation of the reservoir, you can have like a curve. The horizontal could be a reservoir storage, okay, reservoir capacity, and the vertical means the yield. For example, I'm not sure if this is going to be like the linear one or it is going to be like the non-linear, like this curve. So if this is, let's say this is like the 24, and this is the, let's say, what is that? This is the 5.50, 5.45. So I'm not sure if, and this is like the 21, and this is a 5. I'm not sure if this is like going to be like the linear, non-linear, like the concave or convex or something like that. But this is good to just investigate to see what is the behavior or what is the response of the reservoir size and yield. This kind of like a curve is really important. Why? For decision makers. If you are a decision maker, the reservoir capacity has got a connection with the cost, and you can calculate the cost of the reservoir, and the yield is benefit. So the benefit and cost analysis can be easily done by this kind of the curve. So sometimes decision maker can make a decision. I mean, decision makers, like for example, those who are planning for the dam construction, considering all the points. It could be like a consultant, it could be like a client, could be like a policymakers, and see with different yields, you know, you can just benefit more to the people. But with the, you know, you might just have like a more problem with the capacity. As I said earlier, all the discussions, remember, this is not like a black and white, 0 and 1 binary. This is like some sort of gray and fuzzy situation. In some cases, the customers is not true if you say, oh, the largest capacity is the best. Unfortunately, here in this example, it didn't explain other like the aspects. But in many cases, complications is not as simple as this. So you might just have the situation that the reservoir highest, or the reservoir or the highest volume, if you don't have any flood overflow through the spillway, this is bad, because you might sometimes need to just release the flow over the wet seasons, to make sure that the downstream can get the overflow of the flood. But it has to be safely passed. I mean, obviously, I'm not discussing about, for example, let's just have the downstream, or the downstream cities becomes flooded. No, but the flood has to just pass through the system. And in some cases, having the largest dam does not necessarily mean the best. As I said, environmental, and in some and many cases, something important as well. Remember I discussed about the sedimentation. One of the way that that especially the operators can release the sediment from the dam is by using the releasing or opening the gates, or the bottom outlet. Especially bottom outlet is one of the gates in the dam, through the at the time of the flood. Why? Because at the time of the flood, a lot of sediments can be suspended, and it was the best time that you can release the sediment, and you can get rid of the sediment, and you can benefit the environment as well. So nowadays, just please pay attention. The point is not only for the purpose of the taking 100% of the water. In some cases, it might be just apparently, if someone just trying to just take advantage of the water, maybe it's wrong. I say, oh, let's just have some sort of flood, because at the time of the flood, we can release a lot of things with the water. If you say, no, I'd like to just use 100% of the water for yield, for, let's say, irrigation, industrial purpose, whatever, or like the domestic use, and I'm just obliged, or committed to just release only for the compensation flow. And that is not true. Yeah, the fact is that in other times, we need to just release the water for other benefits, as a natural river. So obviously, if you look at this kind of a trade-off between the reservoir capacity and the yield, is not always the case. So that the highest capacity is better. And let's just focus, for example, to this point. And the point here, if someone says, oh, let's just get to this point, stick to this point, this is the best point. No, this is not true. You need to look at here and the cost and benefit, all the cost and benefit, not only the construction and the benefit of the yield. Other the cost and benefit. Maybe in any points here, you might have some other benefits and some other costs. For example, if you have the lower capacity and more floods release, for example, here you don't have no flood at all. Here you have more flood. Okay, so you might be able to just show that, for example, the benefits of the flood to the downstream and fertility of the lands, how you can quantify that one. And on the top of all of them, I'd like to just give you another a level of uncertainty that we have to deal with. That is the uncertainty of the inflow. You're not sure that the inflow that's going to happen, this is the one that listed in that figure, is going to just be your inflow. Unfortunately, the inflow time series is one of the most uncertain parameters that we have experienced. It looks like the rainfall depends on many parameters, as you know better. So uncertainty analysis and inclusions in this kind of analysis is really, really key and important. So just please pay attention to all level of the uncertainty and all level of the beneficiaries in the project like this one. So it's not as simple as once you think, okay, so that's some sort of calculation. Let's see what's the best benefit, and we can just go ahead with that one. So we have the multiple beneficiaries, stakeholders involved, and you need to make sure. And nowadays, especially in the developed country, the voice of the community and the locals sometimes are louder than the decision makers. I know if something goes wrong, the policy makers, they have to resign, they have to change, they have to revert, and they have to completely withdraw the plan because, for example, the locals are really unhappy. And nowadays, you can see with the social media and whatever, which is available even for locals, they can raise the voice easily in the national or international level. So this is something very important that especially make the situation very complicated, because it's not only like the industrial, for example, customers, it's also like to affect a lot of people. So obviously all of these things makes the decisions very complicated. So just I wanted to just give you some hint about all of these points as well. Anyway, so this is like the task for the I think the rest of the presentation I can see is like all related to task 3, detention pond, which is relevant to the things here. These examples, if you remember, this example was the example of the stream. I wonder if you have just had a chance to look at that. But there is a one pond. Here we try to just build this one as a one solution detention pond. Detention pond here can be used to just discharge the flood with a different return period, 2 years, 10 years, and 100 years as well. And it's designed with this kind of level you can see here. This is for the water quality. This is a very small pond at the bottom. You can see here is a profile, and this is the cross section. Then later, this is for 2 years return period is happening in this section. Can you see here? 10 years with some levels in here. Can you see some levels here? 10 years is going to happen here, and 100 years is just going to happen the full capacity. So this is something that designed in the stream for the urbanized area to make sure that we can just convert the urbanized water to the surface runoff to the before development surface runoff, the maximum. And so if you're just going to design the a storage unit or detention pond in this case, you need to just pay attention to some of the when you just have an outlet. In here we have a number 1, number 2, number 3, number 4 outlets, but better, the first 3 outlets are called orifice. Okay, orifice has got this formula, and the 4th outlet is called weir. Okay, weir has got this capacity. This is the weir, and this is the orifice. This orifice is an opening in the in a part, we can call it the orifice. But if you want to just use the orifice has got this formula. Can you see the formula? And this is for the weir. The weir formula for the weir is it gives you the flow rate as a function of the parameters of the C. L is the length of the the weir. For example, it doesn't have a length, or in the weir, sorry, in the orifice we have the A area, cross section of this. Oh, okay, so cross section of this one, not the cross section of the orifice opening. Sorry for that. It has to be. Not sure if this is true. It has to be of the orifice opening. I believe it has to be orifice cross section of here. Yeah, this sounds weird. It's a big question, because the H is the pressure head from the center line of the orifice. This is the orifice to the water level. Okay, and I guess this is I got this one from the user manual of the stream, but I guess this is wrong. This is the typo. No, this is a very simple typo. Anyway, one thing is very important. I'd like to just let you know. First of all, the coefficient. Just pay attention to coefficient. Coefficient for the orifice the 0.65 is very common coefficient. If without having any accurate figure, you can just use this one. Normally, this figure for those of you who've got been in the undergraduate, these figures of the constant figure can be calculated in the experimental works or the tests in the hydraulic lab. For the weir, especially we tested this one in the lab, not necessarily this one, but the crest transverse weir, 3.3. This one is a 0.65. One thing is very important: the relationship between H and Q. H, exponent of the H of the pressure head is like the 1.5, but this one is a 0.5, is like the square root. This is the square root of the h. Can you see the square root here? But this one exponent is a raised to the power of 1.5 or 3 second. Okay, 1.5 is like a half. So this one is 3 times more. So this means that 3 times more, if you have like a higher level, you have a more discharge. Can you see? But if it's got like a higher level, the discharge is very limited, to be honest, compared to this one. So the higher level, if the water rises in the like the weirs, the discharge is much more larger. If the like the water level rises in the like the inside the tank or inside the like the reservoir or detention pond, whatever you're just gonna have, the water comes out this kind of like the orifice. Anyway, so this is like I want to just give you some hints. So this is another like the downstream view. You can see this is like the way that we design it, the 3 orifices. Because of the nature of the water, we just decide to just make this one. I mean, the designer decided to make this one like larger, and this is for the weir as well, and that is for the task 3. Okay, I've got a few slides for, oops, discard. I've got a few slides for the other week, week 7. So oh, sorry, it has mainly, it is that week 7 is mainly related to your practical sessions, but there are some like the very valuable things I like to just explain to you here. It won't take a long time. Please just bear with me, because most of them, please pay attention. Most of them, yeah, we've gone through with a lot of them, but I think with a few of them we didn't go through. I believe I explained all of these to you before. But especially there are like a lot of videos. I just highly recommend that you pay attention to the videos as well. So don't wait for me because we don't have a time. I mean, not the time, because we are like delivering remotely. We don't have a time to go with the video. But please just go ahead after or before the class. Just look at the video as well. I like to just give you some like the comments about like some of the things here. So because I didn't go through with some of the slides here, especially the sewer system that's we discussed in the second part of the module that we just going ahead. It's about like the different types of the sewers. You might just have heard this one, but just pay attention that we have like 2 types of the sewer. One is a combined one. If you look at here, combined one, it's really simple, but it's very important as well. Combined one is that both foul and sanitary sewage and surface runoff, no, foul and sanitary sewage are the same, okay? And surface runoff, for example, look at here, this figure and this figure, are just gonna go carry all of the flows of these, carry through the like a one system pipe. So you can see here the sewer from the business or residential is collected with the same like the pipe, and surface runoff is just going to drain the same. You know, you have a drain here, you know, there's a like the roof area drain, and there's a surface drain. You know, drain, you can see all the in the streets, sometimes there's a drain, racks, and anyway, so all of them are discharged into the same combined sewer pipe. Combined sewer pipe has got all of them, and eventually just going to just have there's a pipe intercept, and it just takes the everything to the wastewater treatment facilities. Okay, and the same. This is a dry season. Once you know, in the dry season, these drains are completely empty. However, the only thing that is taken is like the sanitary sewage or sanitary waste. However, at the time of the rainfall, the wet period, this is a dry period. At the wet period, the drain is also is full of the water or the surface runoff, and all of them are just taken to from this pipe, taken to the wastewater treatment facilities, and you know, the wastewater treatment facilities treat the wastewater and discharge the receiving water, but it could be lake, could be like the groundwater, whatever. However, at the time of the rainfall, because of the like the limited capacity of the pipe, those parts that are overflow the capacity can overflow from the weir structure that is called like a weir combined sewer overflows structure, or the weir wall overflow structure. They can discharge, this is like the worst things, they can discharge untreated sanitary sewage to the receiving water body. Unfortunately, especially in the developed countries, we have a lot of like the combined sewer, especially in London, for example. Thames Water is like the main source of water supply. And at the time of the heavy rainfall, untreated wastewater is discharged to the Thames Water, which is not good at all. And Environment Agency, the responsible company, normally find the water companies, like, for example, the Thames Water, if the, for example, based on the frequency and the volume of the discharge of to the receiving water bodies. Anyway, so, and then later, this is a combined sewer, is like a more or less, we can say like the old system. Then later, we had a like a separate sewer. Separate sewers is that surface and the foul sewers are separate, you know, like this one, completely different. So if there's a heavy rainfall, low rainfall, there is no like the mixing, and there is no like the over discharge. So the CSO, or the combined sewer overflow that you can see here, you know, for example, combined sewer overflow CSO, which is a big issue for the combined sewer, is not the issue at all for the separate sewer. And the fact is that because sewer systems are very expensive infrastructure, we don't have any kind of like the time to just fix, you know, not the time, not like the capital investment to just easily fix this kind of like the issues and make it separate. So that is the fact. So there are some videos here. These are like the more related to like the undergraduate level, but please just have a look at them because this is something that we will look at that in this module. But I'm just happy to just go through with that one, but very briefly. All of them have been mentioned in the reference book, but it's like a more for the undergraduate level for the hydrology, for example, or hydraulics. Rational formula to calculate the peak discharge is a function of the CIA, coefficient, surface runoff coefficient, rainfall intensity I, okay, rainfall intensity I, and the area of catchment. This has to be rainfall intensity, millimeter per hour. And also area is just given as a this formula specifically has got these units. Q is like a cubic meter per second, A is like a square kilometer, and I like a millimeter per hour. So this is something that we're just going to use. And the C, the coefficient is between 0 and 1, depending on the perviousness or unperviousness. It could be as high as like the paved area, like close to 1, or it could be as like the park or the playground close to 0. So that is things. And just pay attention. The catchment is like the outlet point that we're just gonna see all the time if you remember from hydrology. And all of them, the time of concentration is the time that the rainfall from the most remote like the points of the watershed get to the like the outlet or the outlet points of this point that you can see here. This is like called like the rainfall time of concentration. And so anyway, so this is like a procedure to calculate the rainfall intensity. Rainfall intensity is some of the things that you need to just calculate. Go ahead, please just look at these. TC, the time that reach that the most remote part of the catchment arrives to the design point. TC we're just going to use here. So if we want to just use the rainfall intensity, we need to just have like a duration of the rainfall. Duration of the rainfall normally for a catchment, we're just going to use it for the time of concentration, because the time of concentration is the most critical time that all parts of the catchment contribute to the surface runoff of the outlets or the design point. So you need to design based on the time of concentration. Time of concentration has got the two components, T and TF. You can see here, oops, sorry. You can see here T and TF. T is like the time of entry to the sanitary sewage, flow over ground and enter the first sewers, and the TF is the time of the flow over like the sanitary sewage to the design point. So so the TE is given based on the return period based on this formula, like this 3 to 6 minutes, 4 to 7 minutes, 4 to 8 minutes, and 5 to 10 minutes, depending on the like the rainfall. And to calculate the uh, intensity, you need to just use the IDF curve. IDF curve is like an acronym for intensity, duration, frequency curve. So you need to just pick up the duration. Duration has to be like the time of concentration with a return period, or frequency is the reverse of the frequency. And you can easily, for example, for like the, let's say for 50 years, for the half an hour duration, you can easily, for example, here, oh, I'm just gonna to just design for a half an hour rainfall for the intensity of like the 5 inches per hour. You know, inches per hour is like English units, but you can just use millimeter per hour as well. In the reference book, rather than that curve, we have this kind of like a table. This table 12.5 is exactly the same as that figure, but it's like in the tabular format. You know, for any return period, you know, you can see here for any return period, one in 1 year, 1 in 2 years, 2 years return period, 5 years, 30 years, and 100 years. Rather than the curve, we have like the a relationship, and interestingly, relationship is changed for the two types of duration. If the duration between 4 to 20 minutes, it's got like this formula. If 20 minutes to 2 hours, it's got like this formula. And with the following like a return period. If this is like the 2 years, 5 years, 30 years, and 100 years, you use a relevant formula. Okay, so this is something you had this one in the undergraduate level, so I'm just going to pass it on through as well. So, and see the coefficient, you can just use any kind of like a recommendation by some of the like the things recommended by this company. This company, HR Wallingford, is like a company pioneer and preceding all of these kind of like the coefficients for the rainfall runoff modeling. Example, that is, it has some like assumptions that you can see in this kind of like cases. Something very important is that in here you can see the like the online and offline storage tanks. This sounds to be very interesting. So the difference between online and offline. Once you have a flood, you know, for example, you might just have a in a for example residential area, you might just have a flood that can just come to here and get to this peak. This is like the variation of the discharge over the time. That is called hydrograph of the flood. It might happen to this point and eventually have a like increasing and decreasing trend. But something very important, your channel or your region, you might have a specific capacity of transferring the discharge, which is exactly here. Anything above that level, this kind of like a hatched or dashed area, is completely converted to like a flood. So if you have an offline or online storage, you should be able to, if you get rid of this area, or if you store this area, you can easily get rid of the flood. You know, the flood, how disaster or catastrophe it is. So you need to just get rid of that. So by using the storage, you can just use that one. But what's the difference between online and offline storage tanks? Online is something that is built into the sewer. You know, for example, you have like a sewer, you can make it like the inside the ground, and under the ground you can make a tank like this. And let's say we remove walls. The pipeline, rather than circular, you can have like a very big like the tank storage in underground. This is called like the online storage. Okay, offline storage is that you can you don't have such a things. This is like the let's say your pipe, but you can use you can allocate some area apart from the like a sewer system and overflow or divert the sewer. I mean the sewer, what I'm saying, like a surface runoff, for example, not the sanitary sewage. You can divert at the time of the flood to that area that is originally used for other purposes. It's not used for the like the flood mitigation. For example, let's say it is like a football pitch, or if it's like a playground, you know. But at the time of the heavy rainfall, the flood can overflow to that kind of like the pitch, you know, and that pitch can just mitigate or attenuate the flood. So this is called offline storage. So see the difference between online and offline, and offline could sounds very good and interesting, because you can just use that area for other purposes. Parking lot. Sometimes the parking lot is used as a like the offline. It doesn't matter. You don't need to just use it for like the 1 or 2 meters. Even if it can have like a capacity of like the half a meter, it's good. But you need to make sure that if you want to just use one area for like the offline storage, you need to make sure it has a proper storage. For example, let's say it has a like the height of the meter. If it's like for example, football pitch, or like any kind of like the pitch, like the sport pitch is going to be used, you need to just make sure that area does not have like any opening. It has to be used, and it has to be honest, safe as well. For example, you shouldn't just make it like the reservoir that potentially can have a capacity of, or the height of like a few meters. Based on health and safety, once you're just going to design health and safety, is a key points that you need to just make sure that is going to be respected. So obviously, if there is something that few meters, you should say, okay, I'm not going to use that one, and try to just make the maximum height of like a couple of meters, or not couple of meters, sorry, it could be like as high as the like the normal human depth, like let's say like a minimum 1.5. 1.5 is like a safe depth. And if someone just dropped to that kind of like the water unintentionally, it's not like the life threatening. So just this is really, really important. If you're just going to design like the offline storage with like the maximum of depth of like 2 or 3 meters, at the end of the day, you might just attenuate the flood, but it has a like the hazard, serious hazard for the people, for the residential and locals. If someone just dropped that kind of like the storage, that's like the very dangerous, and you might have some sort of like a little liability. And you need to just make sure, if you're just going to design something, you have to just pay attention to this point, that the storage depth has got a like enough like the height, unless you inevitably have no choice than to go with that one. But in that case, you need to just provide all the like facilities, everything, signposts or gate. For example, it has to be fenced, or it has to be like surrounded by area that can be strictly protected, at the time of the flood. But this could be like a bit challenging, because at the time of the flood, no one knows where to go. For example, you say, oh, operator has to just close the fence, or and blah blah. But at the time of the flood, you might see that the operators disappear, and you need to just make sure everything is controlled automatically or automated. So these are some important points that you need to just pay attention. Okay, so there are some guidelines here that sometimes you're just going to give once you're just going to design everything. So please just have a look at all of these points here. The minimum velocity like a 1, and the roughness like the case like the 0.6 millimeters. If you design like a manhole, we have some sort of like the recommendations, and we need to just pay attention to all of them as well. So please look at these as well, all of the points. So I think I discussed all other like the points here. So let's just get back to see. Yeah, I think I just went through with all of them. Next week, we're just going to go through with some examples for drainage system design and see how it goes. But please, in the meantime, try to just install the software, the Stream software, and try to work with the software as well. And also work with your project as well. If you have any question, problem, please feel free to let me know, and we can discuss about this as well. I'm very happy to discuss your project and any progress that you have, or anything that you want to discuss later. Is there any question? Yes, please. Nini, please. Unmute your mic, please.
Yes. Sorry, sir. Can you please go through example 2?
Go through example 2. Okay, sure.
Yeah.
Absolutely. I will go with that one.
Yep.
I think yeah, someone else just tried to raise a question. Amara?
Yes, sir. I'm asking about the AppNet.
Yes, yes.
Yeah, I couldn't get the values of the pipe roughness coefficient, just get the cast iron pipes with age, but not for the
That's
other
why.
pipes.
Not with the.
Not for the other pipes with their ages.
Okay, so let me just search all together so you can see the screen. Pipe roughness coefficient table. For example, here, so you found some sort of like the pipe in some references, but you couldn't find the. Is there any with any type of the pipe without the age, or you could find some of them with ages? Which one did you couldn't find?
Just for the cast iron pipes. I got it.
Yes, makes sense. For example, I just searched it and this is the first link I found it. For example, can you see here, galvanized like the steel, PVC, everything. Some of them, can you see? It says that it's just going to change, but just bear in mind this is a K, not like necessarily the one that you're looking for, because you might just. I think sorry for that. This is something that you can just go ahead. I didn't mention you have to go with the Hazen Williams or any other things. So it means that, for example, could be one indication that the plastic pipes or other pipes does not change. The pipe roughness of roughness coefficient of those other pipes are not changed over the time. That might be one reason for that, but I just leave it to you to just go and investigate later, because it's not like that this is a controversial. Sometimes they might say no, it could be changed, but in some cases might be say okay, no, it's not gonna change. So I've just seen all these kind of like the aspects as well. Okay, is that now clear?
Okay, sir. Thank you.
No problem. I mean, but this is good that if you can have some sort of finding, it's good to just mention, as because you just did some sort of like the investigation for that, and I just recommend that you look at the references as well. I mean, in the references you can just look at the references and see what is the references, and in like if you go to the library, where is the library? Not sure if this link works, but anyway, so the library, anyway, the library doesn't work here. I don't know why, but I think they changed the link. Okay, the library, in summary, you can just type pipe roughness coefficient. Can you see? This is some sort of this, I think, not sure if this is, yes, online can be seen. This is a, sometimes you can just investigate in these kind of like references. Please just use all of the references that you might have. Is that clear, Amara?
Yes, sir.
Okay, no problem at all. Okay, so let's just look at the Nini just asked a question about the example 2. I'm just going to go through that example. Where is that? Okay, so okay, so can you see? Oops, no, not here. No, not here. I think this is a. Okay, so if you look at example 2, so let's just see and look at here like that. We're just going to use the same data of example 1, draw a mass flow curve. The mass flow curve is the one that we plotted in Excel as well, and determine the surge required to meet the given demand. So this is something that we just draw this one, and we want to show like the AB, the vertical distance between the highest difference. So it's going to be the demand. This is something that we want to just calculate, And the section B says investigate the maximum possible demands that could be obtained and any additional storage required. Okay, the requirements. So if you want, it's currently, you can see this amount. I mean, in February and March, amount of water is wasted. AOC is the line here, is the demand. So if we want to just use all of the water, we need to just use, rather than the OC, the demand line has to be OD. So it has to be diverted to the top. So, and that amount needs to be used as well. The dashed line is like a new line. If the dashed line is a new accumulated demand line, obviously the largest difference between the vertical difference between the demand and or the outflow and inflow is like the line A to E rather than A to B. So A to E is like the new line here, and that kind of like the difference or the vertical difference like the 24.6. Okay, so this is the way that we're just going to calculate. And the demand, what is the demand, is that in Excel file that we have in here, oops, it's like the 75.1 is like the total inflow. We used to have 69.72 as a result of like the 5.81, but here we just say all of this water is going to be used 75.1 but divided by 12, average of the 6.25 rather than 5.81. If we're just going to use 6.25, if we're just going to take away the compensation flow, which is like a 0.81, remember, is 5.45.
So,
Yes,
compensation flow always 0.81 or?
Yes, this is the one that's given in our example. This is the this compensation flow did not change. This is something. Where is that? Compensation is a constant, and for question B or example 2, that compensation flow did not change.
Okay, sir.
Yeah.
Yep.
Okay, so let's get back to this one. So we just taken away, and we said the yield, the net yield is like a 5.45. That's it. And the one that we're just going to do, we repeat the same procedure that we did to calculate the one by using the Excel calculation. Rather than 5.81, we use 6.25. I just changed this one, and the same procedure applies. And I will make sure that I put these files in the everything's in there. So let me just have a look, and if not, I will definitely make sure it will be there as well. So no, anyway, so I'm just gonna keep it here. Is that clear?
Yes, sir, clear. Thank you.
Okay, no problem at all. Okay, yes, the Excel files is in there. In week 8, by the way, in week 8, the Excel files in there. Example masker 1 is there, so everything you can see here. So please just, by the way, make sure you can just look at all like the video files that we just put it here before the class. They are very useful, like the files, and those like the PDF, not the PDF, like the YouTube files that is available in the like the video of the presentation. Okay, is that clear, Nini, as well?
Yes, sir. Thank you.
Okay, no problem at all. Okay.
For example 1, do we need to draw this bar chart as well, or only the table?
I couldn't catch exactly. Say again. Sorry.
For example 1 answer, we just need to put the calculation of the Excel, or do we need to put the charge as well?
Oh, no. You can, for example 1, no, you can just do everything because it was not required. You can just do everything by Excel. So this is, I wanted to just give you more details, and that's the reason I just plotted in Excel. But if you don't need to just plot the figure for example 1. But it's only for the purpose of demonstration. I wanted to show you how it works. But if needed, I think it's good if you're just gonna plot that sort of this for your information. This is only for your demonstration. I just put it, and for education, I just put it here.
Thank you.
Okay. Okay, no problem. If you have any question, just please feel free to ask me even after the class. You can easily email me, and I'm sure I will make sure to answer you very quickly. So let me just stop recording here. So if there is no question, so I can just